All right, you guys, it's been a long time coming, but I finally wanted to start talking about 6.2 problem number 4, which is a doozy. And again, you don't need to know anything quite like this for your test here on chapter 6. But I thought this was a really interesting problem, and I did assign it, and I had you do it at the end. In the old days, I used to just have people go in order, and then, oh my God, people just got the life sucked out of them when they got to the fourth problem and ran into something this difficult. They want us to come up with the volume of this little wedge here in 3 different ways, integrating with respect to the x-axis, the y-axis, and the z-axis. But of course, here's the really funny thing about it, and we're going to do all of those, but you don't actually need calculus to come up with this answer right here, because this shape is a simple solid that geometrically we know a formula for, and you can do it this way if you're good at geometry. Which I am, and you guys probably were, but I'm not sure if you still are right now. This, everybody, is a triangular prism. And the formula for the volume of a prism, you may or may not recall, is actually a really simple formula, capital B times H. Capital B means area of the base, and H means the height. And in this prism, let's not make the mistake that a lot of geometry kids make of thinking base has to be bottom. In a prism, the bases are the 2 congruent and parallel polygons on opposite ends of this figure. So these 2 triangles here are your bases, and your height runs in between those 2 bases right there. So what are we doing here, guys? Again, capital B means area of the base. So we've got to come up with the area of this triangle right here. And that is going to be 1/2 times, just in the triangle now, a base of 6 and a height of 2. So all of that is capital B. H, the height, doesn't always mean up and down. Height really means more the depth of the prism, or the distance between the 2 parallel bases. And that's the 4 where I drew the red arrow there. So what happens here, guys? The 1/2 and the 2 cancel out, and ta-da! 24 cubic units is the volume of that figure. Okay, look, that's the answer. And we got it doing geometry, and guess what? It's right. We're now going to do it using calculus. 3 different ways, and I hope you know where I'm going with this. Every single time that we do it, we better end up with the exact same answer that we got right here. Because calculus being right doesn't mean that geometry was wrong, okay? It's just different ways of getting the answer. So they asked us to do this problem in 3 different ways, and I wonder why they did it in this order. I'm actually going to skip around, and the one I'm going to do first is the one where they ask us to integrate it with respect to the y-axis, which is this one right here. Or with the way that they put it, guys, cut with slices perpendicular to the y-axis. So what I've done here, I think you guys can see it, I want you to envision this wedge here as a big block of cheese. And there are different ways that you can slice that cheese into smaller pieces. And the way that we're slicing it in this problem, as the directions say, is we're making our cuts perpendicular to our y-axis. And when we do that, I kind of gave it away right here, I hope you thought about it at least, when we make those cuts perpendicular to the y-axis, I made 3 of them here in red, every one of them is a triangle. Now, what's really weird about this problem, and what makes this the easiest of the 3 that we are going to do here, is that every one of those slices, if you cut your wedge of cheese in that direction, is exactly the same size. And I think you guys can see that with those 3 red triangles that we have drawn here so far. Regardless, I've been telling you guys for weeks now, and once we've started 6.2, and it's still true, that every single volume problem we have is going to use the exact same formula. And the hard part is coming up with the cross-sectional area formula. Well, for us, everybody, each one of these cross-sections, as I'm sure we can see here, is a right triangle, looking something like that. So I'm going to start off with the formula here for area of a triangle, which is simply, not that, there we go, which is simply going to be 1/2 times its base times its height. Well, what I'm hoping you guys notice here is no matter which of those 3 triangles we look at, or any of the infinite other ones that we could draw, they all have the exact same base right here that is equal to this side here. Each one of them has a base of 6. So this is going to be 1/2 times a base of 6. Furthermore, each one of them has the exact same height here and here and here, and they're all equal to this side right here, which is 2. So this is peculiar. Every one of these triangles is exactly the same size, and the area of each one of them is 1/2 times 6 times 2, which is simply going to be 6 square units for the area of every one of these cross-sectional slices. Now, I can't remember a problem that we've done together this year here, guys, where the cross-sectional area formula ended up being a constant. Now, when that's the case, that's your way of knowing you really didn't need calculus to do this problem. There was almost assuredly a geometric formula here when all of your cross-sections were the same. But regardless, this is the formula for the area of each cross-section. So now, everybody, again, trying to be consistent, every problem we've done has worked the same. The volume here has been a definite integral, and in this case, since our slices are going perpendicular to the y-axis, this is a dy integral. Okay, your cross-sectional area formula is your integrand. And again, it's different in every case, but in this one, the cross-sectional area formula is a constant. It's just a 6. And the only thing we're missing now, guys, are limits of integration, the lowest and highest values of y in this region. Well, I didn't talk about this at all, but this point right over here is where the x-axis and the y-axis and the z-axis all intersect. And that's where this solid begins at a y value of 0. And then if we just proceed up the y-axis, it ends right over here, and that red segment I just drew sure looks congruent to this red segment right up here, which we know has a length of 4. So this solid ends at a y-coordinate of 4. Okay, so we don't do this often, but we're integrating a constant. What happens here, guys? We are now going to end up with 6y evaluated from 0 to 4. So the 6 times 4 is going to give us a 24, minus the 6 times 0, last I checked, is 0, and there it is, everybody. 24 cubic units for the volume of this solid if we took our slices perpendicular to the y-axis. And sure enough, that's the same answer that we got when we used geometry. So, again, I want to be clear with you guys, this is a very unusual example here. It was actually much easier than the two that we're about to do. What made it unusual is that every single cross-sectional slice was congruent. They were all exactly the same size, so our cross-sectional area formula was actually a constant. Okay, now I'm going to go back to the first example, or the first thing they asked us to do, which was to cut slices perpendicular to the x-axis. And that is what this is going to look like. Okay, if you guys can't tell, I AutoCAD'd this drawing a little while ago, it was a couple years, and decided to make a big smart file out of it because I knew this one was a tough problem to understand. Now, the plot thickens here a little bit, and I'm hoping you guys can understand where these slices came from. Here is our x-axis coming right down the way here, guys, and the slices cut perpendicular to the y-axis shoot back in the y direction like this, but they also go up in the z direction like that. And what I think you can tell makes this problem harder than the one that we just did, those 3 cross-sectional slices that I drew for you are not all congruent. However, they do all have one thing in common, and I think you'll notice this right away. They all have the exact same base. Here, here, and here, all of those have the same base of 4. So that's something. But it's their heights that are all different. This height, and this height. And that's where this problem is going to become a little bit more difficult. So that's what we're working on. First thing I should say, and I kind of skipped over this last one, if we're cutting our slices perpendicular to the x-axis, this is a dx problem. And our cross-sections here are all going to be rectangles, as I think we can see. So we need a formula here, guys, for area of a rectangle. So let's start off with something simple. Base times height. More good news, everybody. Every one of those rectangles, as we said a moment ago, has the exact same base of 4. But the hard part here is that their heights are all different. And that's where we're going to have to be a little bit creative. The heights of those rectangles are determined here by these 3 points that I'm putting here in purple. And if you look there, guys, those 3 purple dots all have the same y-coordinate of 0. So that's not interesting at all. But they all have different x-coordinates, and they all have different z-coordinates. So what I am going to do here, everybody, is I am going to draw in green here a line segment, the line segment, that contains all of those purple points right there. And I want you guys to notice that green line segment connects which 2 axes? It connects the z-axis on top and the x-axis out here on the right. So I didn't deal with this at all in the last example, but this little 2-dimensional graph that I have over here, I'm going to draw that green line segment on this graph. My z-axis is vertical, my x-axis is horizontal. And the line that I'm going to draw starts with a z-intercept of 2 right there, and it ends at an x-intercept of 6. So I'm going to go ahead and draw that one line segment. Oh God, that was terrible. Sorry. That one line segment that connects those 2 green dots. Okay, and what we're trying to do here really, guys, is we are trying to figure out the z-coordinate of each one of those points there. But of course, they're all different. But essentially, z, I'll just make it really big right there, z is the height of each rectangle. But since we're integrating with respect to x, we need to find a way of expressing z in terms of x. So that's the challenge, and that's what this graph over here on the right is for. And I'm going to ask you to do something that technically you've never done before, but I think you're going to realize right away it's pretty easy. I'm going to ask you guys to come up with the equation of this line right over here. And writing equations of lines is something you've done forever. The only difference is, instead of an x and a y-axis, this is an x and a z-axis. So normally you would tell me this line is y equals, your slope is -2 over 6, so that's -1/3 x, and your y-intercept of 2. So normally you would write this equation as y equals a -1/3 x plus 2. Well, guess what? 90% of that is still correct. But instead of your y-coordinate being given to you by that expression on the right, that is now your z-coordinate. And this line right here, this equation right here, gives you the connection you were looking for. It allows us to take a z-coordinate and express it in terms of x, which we have to do in this problem because we're integrating with respect to x. So the area of each one of these rectangles is going to be 4 times, not z, but a -1/3 x plus 2. Okay, and they didn't make our lives easy here, guys. I could have made this a little bit smaller and easier to fit. But anyway, what do we get here? That is going to end up being a -4/3 x plus 8. That, everybody, keep reading this backwards, is the area of each one of your rectangles. 4 for the base, and then the -1/3 x plus 2 for its height gives you this for your cross-sectional area formula. And now that we've got that, let's get to it. Volume is going to be the definite integral, in this case taken with respect to x, of your cross-sectional area formula, which we just worked on, is a -4/3 x plus 8. And our limits of integration now, this time, are the lowest and highest values of x in this region. So again, here's your x-axis shooting right down here, guys. This thing begins right there at an x-coordinate of 0 and ends right here at an x-coordinate of 6. Whew, that was fun. So let's see if we can't slide that around just a little bit. That took up less room than I thought that it would. I'm going to move that up just a little. Let's go back to blue here. Nope. There we go. And let's see what we can do, guys. Volume equals. I got a good feeling the answer is 24, or at least I hope so. So anti-differentiating right here, that is going to become an x squared divided by that new exponent. That's going to get us a -2/3 x squared plus an 8x, all evaluated from 0 to 6. So what's that going to do for us, guys? Negative 2/3, 6 squared is going to be 36. I'm sorry, I forgot an x right there on my 8. Antiderivative of the 8 would have been an 8x. So let's see, 36. 2/3 of 36 would be 24, and the opposite of that is negative 24, peculiar. But plus, the 8 times 6 is going to get us 48. Minus, let's not forget, all of that comes from the 6, but when we put a 0 into either of these terms, we're going to end up with a 0 there. And lo and behold, everybody, negative 24 plus 48 minus 0 is going to get us 24 cubic units, and that is exactly the answer we were expecting to see. So, quite a bit more complicated here in this example than it was in the second one where we did things perpendicular to the y-axis. This one, being more complicated though, I would definitely say this is a more typical example because your cross-sectional area formula was actually a function containing the variable x. Okay, what I would really like to encourage you guys to do right now, if you've watched this so far and you feel like you get what's going on, I'd really encourage you to pause this video and try to do the third example on your own where your slices are being cut perpendicular to the z-axis. I'll give you a hint, the answer is 24. I don't think that's the problem right there. But see if you can make a little bit of progress doing that one on your own, and I'll tell you that that example follows this one, the x-axis one, a lot more than it does the second. So maybe pause, give that a shot. Okay. Hopefully you did that. Let's take a look at what's going on here and we'll work through this one together. Your slices are now running perpendicular to your z-axis. And this one I'm hoping is easy to understand. The z-axis always runs vertically. So a slice cut perpendicular to the vertical axis would have to be a horizontal slice. This is a dangerous way to cut food, everybody, with your hand on top of something and a knife going through it. But anyway, that's what's going on. So, what shapes did we make? We cut the top off our triangle here, our wedge here, and we formed rectangles yet again. So, I'm going to be doing something similar here to what we were doing just a second ago. Not that. We're going to be doing area of a rectangle, which is still just going to equal base times height. But I guess I'm a little out of order here. Since we're going perpendicular to the z-axis, everybody, this one is going to be a dz problem. Yeah, let's do that. Okay, so let's talk about this, guys. For each of these rectangles, however you want to consider the base and whichever one's the height, it doesn't matter. But what I think you noticed again is that once more, all of these rectangles have the same, I'll call that the base. Again, doesn't matter which is which, but each of them has a base of 4. And the height of each one of those rectangles, as it were, that and that and that, those are my heights. Those are all running in this direction, parallel to the x-axis. So the x-coordinate of those points right there, that x-coordinate, that x-coordinate, that x-coordinate, those x-coordinates give you the height of each one of those rectangles. So the 4x is correct, but we've got to get that x now expressed in terms of z. Now, this is going to sound familiar. You'll notice those 3 purple dots that I drew, just like in the last problem, are all found on this line segment right over here. So you know what I'm going to have you guys do again, z-axis and the x-axis, and here's the exact same line segment again. And guess what? The equation hasn't changed. Z is equal to a negative 1/3 x plus 6, except there's one big fat problem. That equation is solved for z in terms of x. But since we're going to be integrating with respect to z here, we need to solve it now for x in terms of z. So how are we going to do that, guys? I think I'll bring the 1/3 x to the other side where it'll become positive, and then I'll do a negative z plus 6 here on the right, and then I'll multiply everything by 3. X is going to equal a negative 3z plus 18. That's a little messy here, but that's really the same relationship between x and z that we had back here in the dx example. It's just that in that one, I needed everything expressed in terms of x. And in this example, we need everything expressed in terms of z. So back to where we were a moment ago, our formula for the area of each rectangle is going to be 4 times your x-coordinate of negative 3z plus 18. Okay, and I guess it's not that much work. Let me go ahead and distribute that to get a negative 12x plus 72. It's a lot of work to write it, but a negative 12x, excuse me, that's a z, not an x. Oh, that's going to get complicated. Okay, a negative 12z plus 72. Ugly. That's the area of each one of those rectangles. So now, guys, our volume formula comes from taking a definite integral. In this case, we said with respect to z. Our cross-sectional area formula is what we just worked on, negative 12z plus 72. And the limits of integration are now the lowest and highest values of z. Here's our z-axis. This region begins at a z-coordinate of 0, and it ends right there at a z-coordinate of 2. Okay, let's see where this gets us, guys. All right, integral of a negative 12z is going to be a negative 6z squared, and the 72 is going to become a 72, and I won't forget the variable this time, 72z evaluated from 0 to 2. So let's put the 2 in there. 2 squared is 4 times negative 6 is a negative 24, and plus, that's 72z, I think we got a problem here, guys, is 144. Minus, everything on the 0 is going to get us a 0. This isn't good. Let's see here. Something went kablooey because that answer is way too high of 120, and it should have been the same 24 that we had a while ago. So let's see what I could have goofed up here. Each of those bases is 4, so that's right. I'm guessing my problem might be here. So I'm going back to the drawing board right up there, guys, and we had z is equal to a negative 1/3 x. Oh, that's my mistake. Instead of a plus 6, yep, that was a plus 2. Okay, pretty easy to fix though, everybody. That was a 2. When I multiplied that, let's see, that 6 was a 2, and times 3, that should have been a 6. Oops, my bad. So let me go to red right here. That's what teachers do. So instead of an 18, that should have been a 6. Instead of a 72, that should have been a 24. Which I can't quite fit on the edge of this thing. Okay, 24. This then becomes a 24z, and instead of a 144 right there, 24 times 2, this seems more reasonable, is going to be 48. And the negative 24 plus the 48, aha, is going to be 24 cubic units. Whew, a little nervous there, but we came out okay. So, the big takeaway here, guys, of course, we came up with the volume of this wedge 4 different ways. Geometrically, integrating with respect to y, or cutting slices perpendicular to the y-axis, cutting slices perpendicular to the x-axis, and cutting slices perpendicular to the z-axis. And despite my best efforts to screw it up, we did end up with the exact same answer for all 4 methods. Given the choice, use the geometry method. But of course, that won't always be available to you, everybody. So heads up for that one there. Whew. All right. That was a fun problem. Hope you guys enjoyed it. And yeah, there we go.